This video is going to give an overview of case control studies. There's a video I just did that kind of compares and contrasts case control studies and cohort studies. But yeah, this one's just going to give an overview of case control studies, and it's a really broad topic, so if I was to cover everything to do with it, it would take several hours. So basically, like I took some of the distinct topics and I'm going to give them other videos, like comparing case control and cohort studies, principles of control selection, matching, and biases in case control studies. The gist of them will be covered in this video, but other videos that I'm going to make will cover them a little more in depth. So with case control studies, you're generally sampling from a population. This is an example of a population that's, say, like a city, or a sample from a city. So the first thing we do is, from our roster of people where we have access to them, we figure out who's disease positive and who's disease negative. And from the disease positive people, we basically set them aside and we keep them because we want to make use of everyone who's disease positive. With case control studies, you're typically working with really rare diseases. So pretty much every single one of these disease positive people are valuable to the study. Disease negative people are typically a lot more common with rare diseases, obviously. So we have this large group of people here, and we're basically going to take a random sample of them and use those as our control group. And what we're hoping happened here is basically that the in both cases, we're taking people out of the population without any regard to their exposure status. We basically have this group of disease positive people, and we need to compare them to something. So we compare them to people who don't have the disease. And our intent is to figure out if you're more likely to have the exposure if you are disease positive than if you're disease negative. So ideally, this group that we pick represents the baseline exposure distribution of everyone. And basically, we're trying to figure out if you're a disease positive, are you more likely to have been exposed than if you're disease negative, basically. So yeah, we compare exposure status. And that's what that would kind of look like. You're usually kind of asking about their exposure status in the past. So people are outlined in green here. Were exposed at some time in the past. The time that you're asking about depends on the nature of the exposure and the disease. But we'd have some pretty good evidence that the exposure leads to disease if the exposure is much more common in the disease group. So just kind of reiterating those basic ideas, with a case control study, you seek out those cases purposively because it's a rare disease. And basically the efficiency of this design is you don't need to sample and hope to find cases. You go find them purposively. And that sounds weird because it's unrepresentative of the population as a whole, but the reason it's okay is because we have no regard for their exposure, and selection bias needs to be related to both the exposure and the outcome, and we have done something just related to the outcome, so it's okay. You sample the non-diseased individuals from the population that gave rise to those cases, and you compare the exposure status. And a big way that this differs from a cohort study is that, at least from a prospective cohort study, is that it's usually using health records. It's usually either finding people's disease records and then asking them about their exposure in the past, or not really interacting with people at all and using the records to find both their disease status and their exposure status. So the most difficult aspect of a case control study is deciding who your comparison group is, who are your controls going to be. I'm going to do a whole video on that, but just briefly, some qualities of a good control group are that they represent the exposure distribution in the underlying population, and they are eligible to have become cases if they had gotten the disease. So some ways that you can pick controls, one of the big ones is temporally, because we would like to be able to pick people who are at risk of getting the disease but didn't, basically. So I'm going to get into those in a second, but incidence density and cumulative incidence are common ways to match on time, basically, or to try to, or at least with incidence density. Geographic, in quotes, is another way you can source controls. Primary source is kind of like what I showed before, where we have this like town that we take a sample from, and controls are that's a primary source, that town, and it's really easy to kind of wrap your head around where those cases came from and where you're going to go get your controls. Secondary source, I had an idea for like an image, so I'm going to show you that in a second, and hopefully that will help, because the idea of a secondary source is kind of hard to wrap your head around. So let's start with those temporal ones. So for an incidence density case control, the basic idea is that if you're looking at hospital records from like 2017 to 2020, you would start with this like population, and as you're following their records forward, you basically like have their exposure status at this point. But this person outlined in red is someone who in this span of time between 2017 and 2020, they became a case, and we add them to the cases, and at that same time we select a control basically from the set of people at risk. And by doing that, basically these two people are matched on calendar time, and ideally that controls for like variability in calendar time and also just time at risk, because the longer you look for a disease, the more likely you are to find it. So basically we avoided that source of bias in the sense that these two people had the same observed time at risk. They had the same, like, without considering exposure, like I haven't written anyone's exposure status, but basically like these two people had the same opportunity to become a case, and this one didn't. So they were selected as a control at that exact time point that this person became a case. Cumulative incidence is a different approach, where basically you like select your cases as time goes on, and only once you get to the end of this study period do you sample from those who didn't become cases, and you choose those as your controls. So this is basically describing like the primary study base, like I did before. This is just the same slides as before. So you find out who's disease positive, you get rid of them basically from this like population. Like we're keeping them, but you're getting rid of them as far as like for the purposes of looking for controls. And what happens now is basically this primary study base is very tangible. Like it would be like a town where you might have like census records or tax records, or just some information about those, like a roster of the citizens basically, and you can randomly sample from that roster. And this primary study base is kind of tangible. It's a town basically. It's a geographic base. A secondary study base is much more nebulous because it's not necessarily defined by geography. This is my idea for how I can represent that. Like an example of a secondary study base is a referral clinic. Who the cases are is a little easier to wrap your head around. Cases are basically those who develop the disease and are referred to that clinic. So think of this not as like the hospital in a town, but more like a specialist where people might travel from like all of the nearby towns to go to like the only like I don't know, like some really like obscure type of doctor. This isn't a good one, but basically like a really good fertility clinic might serve more areas than their immediate geography. You might travel to go to that. So to be a case in this study, basically you need to be identified, that orange person, and someone needs to write you a referral to send you there. And now you're eligible to be a case, and if we have some span of time we're looking at, everyone who gets sent there is basically a case. Yeah, so that person got the disease and were diagnosed and referred. It's a little more difficult to decide who the control base is, because you need to conceptualize who would have been referred to this clinic had they gotten the disease. And who knows, like it's difficult. You could probably say, like, if it's the only one in like a 100-kilometer radius, probably everyone in a 100-kilometer radius, if they got the disease, would probably be referred there. But it gets, like, for example, if this person gets the disease and say there's another referral clinic where they're like a pretty close distance to either, this person might have been better because they're almost perfectly in the middle. But now geography isn't the factor as much, where it's hard to conceptualize if this person is part of the secondary study base of this referral clinic, because we don't necessarily know if they would have been referred here if they had gotten the disease. So I think you're probably starting to get why secondary study bases are difficult, one thing you could do is you could use those referred to this clinic for other reasons. Like if this is like a gastroenterologist, like a stomach doctor, and you're doing like colon cancer as your cases, you could pick someone that was referred to this clinic for another disease. So like, I don't know, like some like IBS or some other disease, and you can be confident that if they had gotten colon cancer, this is where they'd be referred because they were referred for this other disease. One thing you got to be careful of here is the reason that they went can't be related to the exposure, and yeah, that's what stomach disorders was not a great example because I think a lot of stomach disorders have the same causes and things that aggravate them. So like things like like for example, like coffee might be related to like colon cancer and IBS, and the fact that this person is going to a gastroenterologist probably means like either they drink a lot of coffee and that's causing the disorder, or they're actively abstaining from coffee because they don't want to aggravate it. That's a whole other problem, but basically what I'm trying to get across here is like what a secondary study base is and how you conceptualize the control population. Switching gears now, as far as deciding the number of controls per case, because cases are rarer, they're harder to come by, because when you decide to do a case control, you're usually investigating a rare disease. So recruiting more than one control per case is a way to increase power. For example, having 2 controls assigned to every case, or 3 or 4. And statistical power is basically this idea that like the larger your sample size is, the more likely you are to find an association when it's there. Let's say like we know that smoking leads to lung cancer. We know they're strongly associated. But if we were to try and do our own study on that and we only used like 100 people, even though that association is truly there, we might not have enough people to be able to detect it. So that's the idea of statistical power, and because cases are typically the limiting reagent here, where like you have an almost unlimited supply of controls but only a handful of cases, you can increase statistical power by basically increasing the number of controls per case. But something to note is that starts to like level off around 4 controls per case. So going anywhere beyond that, you're just going to increase the number of people in the study without reaping the benefits of that. Basically, you're including them without any gain in statistical power. So you're basically just creating more work for no reason. So some advantages of a case control study is that it's more statistically efficient. That's kind of related to the concept I was just talking about power. Or when something's more statistically efficient than something else, it basically means that it is equally capable of finding the answer, but with a fewer number of people in the study. So like if a case control and a cohort study are both trying to answer the same question, case control can come to the same answer with the same confidence in that answer, but with fewer people basically. Case controls are suitable for rare diseases, so if a disease is very rare and you try and use a cohort study, it might take decades to accumulate enough cases. But the nice thing about a case control is you don't need to wait for cases to occur. Basically, you just use the records of cases that have already occurred and do everything like retrospectively. There's no waiting involved. When the induction period is really long, so like this period between reaching a sufficient amount of exposure and the occurrence of disease, if that's like really long, you're going to be waiting a long time in a cohort study to again accumulate disease. But like I said, same thing basically. With a case control, you don't need to wait for people to become diseased, because by the time you're doing the study, they all already are. Case control can be done quickly. A lot of the advantages for a case control are based on efficiency, so like statistical efficiency, which also translates into like cost efficiency. You use less people. Also, like you can do it just faster in general. Some drawbacks though. There's a decent amount of drawbacks. A lot of people don't trust case control studies, partly because they don't fully understand them, but also because there's some legitimate drawbacks. A lot of them come from the idea that everything's retrospective. So both the exposure and the disease have occurred at the time that you're doing the study. So that means it's subject to all kinds of bias because basically with a cohort study, you're witnessing you might even be witnessing someone go from exposure negative to exposure positive. But by design, with a cohort study, you're witnessing someone go from disease negative to disease positive. But the fact that the disease has already occurred and that people know they have the disease, if you're asking them about their past exposure, which is common in a case control study, you find people with the disease and you ask them about their past. People who have the disease might recall their exposure differently than people who don't have the disease. Where someone with cancer might have thought harder about their various carcinogenic exposures because they're trying to find a reason for their cancer, basically. And this could either make them remember more accurately. It could also cause them to remember things that aren't exactly true. They might overestimate their exposure because they are basically have this idea that of something they think or believe causes cancer, and since they know they have cancer, they might overestimate how much they were exposed to that. Selection bias is when basically this group that we have, we draw a small circle around who we selected for our population, and the population at large differ in their amount of exposure status and disease status, basically. So in that way, those who are part of the study and those who could have been part of the study differ in ways that are related to both the exposure and disease. By the whole nature of a case control study, those who have our study, the distribution of the number of people diseased and non-diseased differ in our study by design from the population as a whole, because we decided how many people have disease and how many don't in our study, but it's not related to the exposure. So in that way, selection bias hasn't occurred. So by design in case control studies, selection into the study is based on disease, but if it's also in some way related to exposure, you're more likely to suffer from selection bias. And cohort studies are pretty immune to that because although we're selecting people into the study sometimes based on their exposure status for a cohort study, it's almost impossible for selection bias to occur because the outcome hasn't happened yet. And in that sense, their inclusion can't be related to their, it can't be related to the outcome, basically. So outcome is classification is another one. There's all kinds of codes we use to classify disease, and it's possible that those codes might differ, and I guess outcome is classification also means the likelihood of someone having their information retained over time might differ, whether you have that's kind of more of a selection bias thing, forget that, but basically someone who has their outcome is classified. That's more likely to happen when you're not witnessing the outcome happening. Basically, if it involves any remembering or if you're relying on the record keeping of someone who didn't do it for the research process, someone who might have done it for administrative purposes in the past, there's definitely the possibility for outcome misclassification in case control studies more than cohort studies. Prevalent cases versus incident cases. So prevalent, that's those who have the disease currently, and incident cases is newly occurring disease. They might differ in fundamental ways that might be related to exposure status, and because prevalent cases are disproportionately represented in case control studies, that could present issues, basically, if it's related to exposure status. And some exposures are best measured prospectively. So some examples are some biomarker that isn't commonly measured in the hospital. You'd be hard pressed to find diseased people and ask hospitals if they happen to have cortisol samples on that individual. That's not likely at all. That would be better to measure that exposure prospectively. Another one is stress. People remember stress incorrectly a lot. It's kind of painted by the context of the event. So for example, remembering how stressful birth was, or the time around birth, you might underrepresent that because of the joy you feel afterwards by having your baby, but you might overestimate how stressful something was in other scenarios. So stress is better measured in real time forward, basically, while they're experiencing it. I'm going to briefly talk about matching. This is another one that's going to get its own video. So if you make the distribution of a confounder the same in cases and controls, you basically have eliminated its influence on the relationship under study. So with individual matching, every case has a corresponding control, and it requires a matched analysis. With frequency matching, not every case has a corresponding individual, but basically we've made it so the proportion of a confound, like the frequency of a confounder, is the same in the case and control group. It'll be easier to see with an example. So this is individual matching, where we have two potential confounders, age and gender. So this is a female individual under 40 who's a case, so we need to find a control that's also female and under 40. This blue person with the red outline is a male over 40, so we need to find a male over 40 that's a control. On the other hand, this is frequency matching, where these blue bars are like the amount of cases in these various strata. So we have two binary confounders, so there's 4 strata: males under 40, females under 40. That should be males greater or equal to 40 and females greater or equal to 40. So we have the percentage of cases that are in each of these strata. So like 25% of the people in the case group fall into this female under 40 category. Basically, we figure out the percentage of individuals in each of these 4 strata and just make sure the controls have the same percentage, basically. Just a quick note on analysis. So the outcome is binary. With case control, you're a case or you're a control. Logistic regression is suitable for this. If the disease is rare or you're using an incidence density design, then you can estimate the relative risk from the odds ratio, which is basically the measure of effect produced by logistic regression. But if you do individual matching, then you need to use conditional logistic regression.